Let us talk about log graphs. Log graphs have got to be one of the greatest inventions in experimental physics and science because they allow you to convert just about any data set into a straight line. As I mentioned in one of the earlier videos, in astrophysics we have a saying you can turn anything into a straight line graph if you use a log graph and a thick enough felt pen. The thing about log graph, the semi-log graph had a logarithmic scale up here, an ordinary scale down here. Log graph has got log graph has got a logarithmic scale up there, logarithmic scale down there. Hopefully you've seen the semi-log video, but if you have, basically these numbers here, you'll notice these are not evenly spaced. So this goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it goes 20, 30, 40, 50, 60, 70, 80, 90, 100, and so on. And if we had another one, it would be 200, 300, and so on. So what this means is if we have a data set, like we have a data set here, I can just enter these numbers straight into here without doing any mathematical calculations whatsoever. And that makes things a lot easier. Like, let's take this data set. The first point I have is first thing we do with a graph, of course, is we make sure it's got a title, log graph for frequency versus tension. We make sure it's got units, labels, tension down here, newtons, frequency up here. What else have we got? What we have to say, I look at my frequency ranges, so tension goes from just under 10 newtons to 50 newtons, or just under 50. So I'm going to call this 1 to 10, 10 to 100. And the frequency goes from 60 to 138. So I'm going to say these are 10s and these are 100s. So you notice I wrote down here, I did this a different way than I did in the semi-log graphs. I said this is 1, this number here is a 10, this is 100. That's an alternative way of writing it. So I can say this starts at 10, these are 10s, hundreds, thousands. And then I enter the data. So the first point is 9916. So without converting these, without using a calculator or anything, I'd go along to here, 9.9. It's just before the 10 up here. And I'll set these 10, 20, 30, 40, 50, 60, and I'll just enter the point, ponk. Then I'll enter the next point, 19.8. The 19.8 is going to be just before the 20. And 86, so we go up 80, 85, just over there. And so I can enter each of the points that way. And just like any other graph, straight line graph, when you're doing a linear graph, you then grab a ruler and draw a line through it. And remember, when you draw a line through 2 points, you should always draw a line through 2 points. In this case, I've chosen probably the first point and the fourth point, or the fifth point. Say the fifth. Those are pretty close. But you choose, remember, it doesn't have to go through the first point and the fifth point. It can go through the ones that you think best represent the line. It's just in this case, I think those two best represent the line. And if you want to find out the intercept of this, because remember, often the intercept is the most important thing, you extend the line down to where it crosses the 1 value. On a normal graph, you do it where it crosses the 0. In this case, where it crosses the 1. So it goes 10, 9, 8, 1. So there is going to be the intercept point. So that intercept point is going to be, what's that about? It's about 2, just under 2. In fact, I worked it out as 19.9. Now, like any other graph, linear graph, once we've got that, we want to work out what the gradient is. And there are 2 ways of doing the gradient. With this, the 2 ways of doing the gradient. If I have a line like this, and I know the first point and the last point, I choose my 2 points, and I can physically draw. Remember the formula for a gradient is equal to change in y over change in x? Well, I can do this graphically, very simply. What I do is, if these are my points, I use a ruler, like that, and I physically measure off my graph. I use my ruler, I measure I measured it to there, and that was 61 millimetres high. And then I measure, so basically I've got a right angle triangle. I've measured that, that's 105 millimetres. And I'm actually just measuring straight off the graph. So I can say the change in height is 61 over 1/5 millimetres equals, this is what they invented calculators for, 61 divided by 105 equals 0.58, well, 1. That's one way of doing it. Of course, as you can probably gather, this way is only as accurate as your ruler. So an alternative way of doing it would be m is equal to change in y over change in x, which in this case is going to be, we take the log values, well, log y2 minus log y1 over log x2 minus log x1. So what I do is I choose my values. I've chosen the first one and the last one. I'm going to take the log of those values. So this is going to be 0.1, this is 0.1, this is 0.2. So we're going to use log 10, so we use log 9.9 equals 9956, 0.9956. Log of 49.5 is equal to 1.6946. I'm always used to doing it to 4 decimal places because I used to use log tables at school. This was a way of doing these calculations before log 60, before they invented calculators. It was 1.7782, and the log of this value, log of 138, is going to be log 138 is 2.1399. Okay, so what's on the y? The y is the frequency, so this is going to be y, and this is going to be x. So basically we go m is equal to log y2 minus log y1 over log x2 minus log x1, which is equal to, well, log y2 is 2.1399 minus log 1 is 1.7782 divided by 1.6946 minus 0.9956, and then we stick that all into the calculator. 2.1399 minus 1.7782 equals, divided by the brackets, the bottom line, 1.6946 minus 0.9956. That's equal to 0.5175. So let's just compare that with our other way that we did graphically, which was 5.81. So this is actually a much more accurate measure way of doing it. So remember, if in doubt, always stick it through 2 points. The 2 points that represent the slope or the gradient, and that will tend to give you the most accurate way of measuring it.